Okay, so apologies for the delay. We'll begin with the webinar now. So good evening, everyone. I am Adya Pandey and I welcome you all to the 18th session of the PSPO webinar series. Today we have with us Professor Prasanna of Management Studies, IIT Delhi. He was formerly a postdoctoral fellow at the Molson School of University. He graduated in the year 2008 as a fellow in quantitative methods from the Indian Institute of Science. His research interests lies in modeling, solving optimization, design problems arising in supply chain applications, goods logistics, urban transportation, disaster preparation, and evacuation. Methodologically, he is interested in discrete optimization and the data, multi-level, multi-objective optimization. Today, he will share with us his work titled Multiple Allocation Hub, Interdiction and Protection Problems, Model Formulation and Solutions. I request Professor Prasanna to begin.
Yeah, okay. Okay. Thank you, Adya. So everyone, can you all hear me? My voice
Yes, sir. You're audible. Yes, sir.
Yes, sir, you're audible.
Okay. 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 Thank you. Thanks for inviting me. Thanks, Professor Bolia, for inviting me to give a talk in the symposium, public system symposium. Here what I'm going to do is I'm going to present my paper on multiple allocation, hub interdiction, and hub protection problems. So this is this problem studies like an interdiction. So interdiction is essentially a targeted attack, right? So like here, what happens is like we are interested in finding critical hubs in a hub and spoke network, and you'll see like what are the applications and how to solve this problem. So the focus of the problem is like not only modeling it, but also we want to solve large scale problems. Large scale problems in the sense like when you look at large data set, these problems are NP hard problems, so it will take a lot of time if you are directly solving it by solver. So we'll also be developing some algorithms to solve these problems, right? So that will be the focus of this work. So without wasting much time, so I'll start presenting my work. Okay, sorry. Okay, yeah. So let me just go to the front. Yeah. So this is the paper, the multiple allocation, hub interdiction, and hub protection problems, model formulations and solution approach. So this is jointly done with my advisors, Professor Sachin Jaiswal and Professor Ankur Sinati, IMA, then Professor Navneet Vidyarthi from John Molson School of Business at Concordia University, Canada, right? So first we'll study what is hub and spoke network. So hub and spoke network is like, suppose you look at a problem where there are like n nodes, and you have to send a flow from each node to every other node, and you have to receive from every other node, right? So like if that is the case, this is like the case of a standard transportation problem. So how many arcs you will create? You will create like n choose 2 arcs, like every node is connected to every other node, right? So this one is not practically possible in a lot of scenarios because you will not be using the full capacity of the vehicle. Because you're not utilizing the full capacity of the vehicle, so like the cost is going to be somewhat higher. So this is direct routing between the nodes. So instead you can propose a hub and spoke network in which you can designate some nodes as hubs and some nodes as spoke nodes. The ones with the red arc is the hub to hub arc. The node, this node, this node, and this node are the hub nodes, and all the other nodes are the spoke nodes, right? So like here what happens is like from spoke to spoke flow, hub connects flow from different spokes, right? And it sends to the next hub, and then it distributes the flows, right? So hub performs the function of collection and distribution. Collection, transshipment, and distribution. Suppose I want to send a flow from node A, spoke A to spoke B. So like spoke A, it will go to hub, this hub, the first hub. The first hub will also collect flows from like multiple spoke nodes. Then this will go here to the next hub. Then it will be distributed, right? So this here, what the advantage is like, you can get a better economies of scale because like mostly this hub to hub flow is like this use a full capacity of the vehicle, right? So when you use the full capacity of the vehicle, so like the cost is getting distributed, and you get better economies of scale. So you will understand this like when we discuss some examples. So this one is a typical network connection, which is called a single allocation. Single allocation means each spoke node is connected to only one hub node. So an alternate case can be of multiple allocation, right? So this is the multiple allocation case where there are each spoke node can be connected to one or two hubs. So here this spoke node is connected to both these hubs, right? So this is multiple allocation. So what are the applications of hub and spoke network? So like this, most of you would have heard this term hub and spoke. So predominantly it is used in airline transportation. Suppose someone wants to go from Nagpur to Jammu, right? So like you cannot send a flight from Nagpur to Jammu because there is not enough demand which can go from Nagpur to Jammu. So in that case, Nagpur will be connected to Mumbai hub. Mumbai to Delhi, there is a transportation. You will go in another flight, then Delhi to Jammu, right? So Nagpur, so like at any point in time, 5 people are going from Nagpur to Jammu. So the flight from Nagpur to Mumbai, which is the spoke to hub, will will collate all the demand from not only from Nagpur to Jammu, but also to all the other flights which are going to Mumbai, right? From Mumbai to Delhi, you will use a very large aircraft. So like here, the demand from Nagpur to Jammu will also go, but also the other demand, which is like Mumbai to Delhi, Mumbai to Jammu, etc. Right? They will also be collected here. And New Delhi, it is again distributed, right? So this is one application of urban spoke network. Another is urban transportation. So you can see that metro network is like a hub network, whereas the buses are the spoke network. The spoke connects to the hub, right? Another is trucking. First mile and last mile delivery, they are typically a spoke component, and truck transportation between this hubs is a hub network, right? And postal operations. So there are sorting centers which can function as like hubs. Hubs are like like a facility which are very large in nature. So they collect these flows from different post offices and they again distribute the flows, right? So these are different applications of hub and spoke network. And also it is used in telecommunication and power distribution, right? So these are the applications of hub and spoke network. So like hub and spoke network, like what are the features? One is lesser cost of construction, right? Because you are having only lesser number of arcs. Whereas in a direct network, you are connecting almost every node to every other node. Here, you are typically having lesser links. And because you have lesser links, there is ease of failure detection. You can easily detect where the node network is failing, and also lesser cost of operations, right? Because you get, you can typically you can see in this case where the subway stations and spokes. So like the metro train can carry a lot of population, right? So like the unit cost of a particular passenger will be very less. So that economies of scale also kicks in when you use a hub and spoke network. So like, yeah, so these are the applications of hub and spoke network. Now let us go to the problem, which is our interdiction problem, right? So like the motivation for studying this interdiction problem on hub and spoke networks is like, since the hub carries lot of amount of flows within the network, the attack and a disruption in the hub can cause lot of disruption in the supply chain network. So like in a yarn, so there is a study which says that just attacking 2% of the airports, right, 64%, 64 in number, is possible to disrupt the entire United States yarn network. Another states that like in a electrical network, knocking out just 9 out of 55,000 substations can result in a coast to coast blackout, which is like east coast west coast blackout. So like even though most of this power distribution systems, airline systems, subway systems, urban transportation are formulated as urban spoke network, because like because hubs carry a lot of flows, and an attack on the hubs can cause a significant damage in the network, right? So that is why we are interested in finding what are the critical hubs in a hub and spoke network. So that is the motivation for our work, right? So we are going to study that. So interdiction problems generally, it means like identification of critical components in a network. So these problems are modeled like a two-level problems. Two-level problems means it's a Stackelberg game. So they're between a defender and an attacker. Defender is the network operator. Attacker is the person who is going to attack the network. So they are bi-level in nature. Bi-level means like you have like max min max type of problem. It's not like a single level optimization problem. And broadly they are classified into network interdiction and facility interdiction problems. So I'll just touch upon this network interdiction, facility interdiction problem. So network interdiction problem is like you want to identify critical nodes or arcs in a network. So one is the shortest path network interdiction problem. Shortest path network interdiction problem is like, so the attacker is a person who wants to maximize the defender's shortest path. So the attacker will remove some arcs in the network so that after the attack of the attacker, the defender has to route the flows through the shortest path. So he wants to maximize the minimum shortest path, right? So normally in the shortest path problem, your objective is to just minimize. So here you want to, like, if you have like 10 arcs, so you want to attack like 3 or 4 arcs among these 10 arcs, so that you want to maximize that minimum arc, minimum shortest path, right? So that is shortest path network interdiction. Most reliable path interdiction is typically used for smuggling and all. So like there is a smuggler who is moving from one part of the network to another part of the network. So he is traveling in these arcs. So each arc has a probability of probability of evasion. So he wants to maximize this probability of evasion. Whereas the the attacker in this case is the government. So he wants to catch the smuggler. The government wants to catch the smuggler. So like, so by attack here, what they mean is like you can put some extra sensors or like surveillance in a particular arc. So like you want to decide like, where and all we'll put the surveillance so that we will minimize this maximal probability of evasion, right? So that is most reliable path interdiction. Maximal flow network interdiction is like the person wants to maximize the flow. The defender, obviously, he wants to maximize the flow, whereas the attacker wants to minimize that maximal flow. So he will attack some components in the network so that that when the particular arc or node is not functional, so you incur a like the maximal, so minimize the maximum flow which happens, right? So that is maximal flow network interdiction. So these are like, just we are just touching upon, right? There are like a lot of problems in network interdiction. So you can study these review papers by Collado and Papp and Smith and Song. So it deals with a lot of papers in network interdiction problems. So it has a lot of applications in disrupting enemy flows, like in counterterrorism, infectious disease control. So like shortest path network interdiction can be directly applied to infectious disease control, counterterrorism, right? So which part of the network will attack so that we make the we'll make the information channel, like, means you create the network, you break the network, right? So like, what is the minimal number of attack you need to make so that you will break the network so that information doesn't pass through among the terrorist organization. So that is another example of network interdiction problems. Like going to facility interdiction. So here you have a facility network, right? So here you are interested in finding critical facilities in a facility, in a network which one interdicts cause a maximum disruption. So here, like I just listed 3 papers. So there are a lot of papers here. So our interdiction, median and covering problem. So here the attacker and defender is there. The defender is the one who is operating the facility network. He wants to minimize the cost of satisfying customers. The attacker wants to attack some facility so that he will maximize the minimum cost. So similarly for covering, probabilistic R interdiction is like the attack has some probability of being succeeded. Then this is called as a fortification problem. So here this is like one level above this interdiction problem, where you know that there is a different attacker who is going to attack your network. So you will want to protect some facilities before that attack. So that is our interdiction median problem with fortification. Coming to hub interdiction. So here, like here you are interested in, like there are again 2 players. There is a defender, there is an attacker. The defender is the network operator. So he has hub and spoke network with P hubs. So the attacker here, what he wants to do is he wants to attack R of this P hub so that he will maximize the minimum cost after attack, right? So that is what we are going to study. So let us go to the problem. So the problem looks like this. It's a 2-level problem. So here the first level objective is to maximize the defender's routing cost. So this is attacker subjective. This is attacker subjective, is to maximize the defender's routing cost. So he wants to attack R out of this P hubs. So once a hub is attacked, the hub can it is not functional, right? So it's a terrorist attack or something like that. So it is no more functional. So now the attack has happened, right? So the defender, the next level, he wants to satisfy the demand which is disrupted through the remaining surviving hubs, through the surviving hubs. So the surviving hubs are P minus R. So initially you had P hubs, out of which the attacker is attacking R hubs. So remaining P minus R hubs, the defender has to do this minimum cost routing, right? So the attacker wants to maximize this post-attack, post-interdiction routing, right? So that is the nature of this hub interdiction problem. So this problem is like this. So Wij is the demand which needs to be transported between nodes I and j. Distance, so Dijkm. So I and j. So here 2 and 3 are the hubs, right? So Dij23 means, so I is the source, j is the destination. I is connected to 2, hub 2, 3, then j, right? So this is the path. So you have alpha, delta, and gamma. So these are called as coefficient of transshipment, which is normally given to hub and spoke network because you get this economies of scale. So this is typically less than 1, right? So like then P is the number of hubs in the system. R is the number of hubs you want to attack. The attacker wants to attack. N is the set of all nodes. H is the set of all hubs. So you can see that H is a strict subset of N. So N, cardinality N is the total number of nodes. P is the cardinality of H, right? So out of this P, I want to attack R. So this is typically the flow which happens, right? So here I is the source, J is the destination. So you are connected to 2 is the hub, 3 is the hub, and then you go to J. So this is how normally it happens. So what are the variables? There are only 2 variables, ZK. ZK is a binary variable. It says like, 1, if a hub K survives interdiction, which means like if a hub is not attacked, right? If hub is attacked, ZK is 0, right? And XIJKM is the fraction of flows from source I to destination J through hubs K and M in that order after interdiction, which means I, K, M, J. If this flow is happening, then XIJKM will take some value, right? So that is what this means. So this is fraction of flows. Fraction is like, it's a number less than 1. So if a flow from I to J is distributed between 2 paths, then it is 0.5, 0.5, something like that, right? So if entirely it is flowing through a single path, it is like XIJKM will take value 1. So what is a model formulation? The model formulation looks like this. So here the upper level problem is this, right? So this is the upper level problem. This is the attacker's problem. Attacker, this is the defender's problem. So the attacker here, he wants to maximize Z subject to P minus R hubs. So he needs to, there are P hubs out of which he needs to leave P minus R hubs, which means he's attacking R hubs, right? So Z is given as this. Z is minimize Wij, Dijkm, Xijkm. Dijkm is the cost, which is routing from I to J through K and M. Wij is the flow. So it's a flow weighted cost. So you want to minimize this cost. So the first constraint, summation Km Xijkm is equal to 1 implies the fraction should be like, should be equal to 1. So for every Ij, for every source I and destination J, the total flow through this different hubs should be equal to 1, which means the entire flow should be satisfied. The second constraint states that if a hub is surviving, then only a flow can happen through the network, right? So you cannot route a flow through an interdicted hub, right? So that is what this constraint says. So this is the attacker's problem. This is the defender's problem. The attacker wants to maximize Z. Z is the defender's objective of minimizing the cost. So it is maximize the minimum cost. Now this problem is a 2-level problem, right? So you cannot directly solve this problem in Cplex or any software. You cannot solve this problem because the software will not take it because there are 2 objectives. So you need to, as such, even if the lower level problem is an LP, this problem is like an LP, right? Xijkm is greater than or equal to 0. Then also it is shown to be NP hard problems. So this is like an MIP. So the upper level is an integer problem and lower level is an LP. So this problem is an MIP. It is a very difficult problem to solve, right? So one way of solving this is like you can enumerate all possible P minus R combinations at the top level, and you can solve this problem and you will take the maximum of this. That is one way of solving it, but that will take a lot of time, right? So that is where like we are stuck up. So like what we will do, like we will be reducing this problem. So it is a bi-level problem. So we will be reducing it to a single level problem using some reductions, right? So one reduction will be using as dual decomposition, which is like you take the dual of the lower level problem. The other is like you imply, we use a sort of constraint which is known as closest assignment constraint, which is going to replace the functionality of the lower level problem, right? So dual decomposition is very simple. Like, you look at this lower level problem 4 to 7, this is an LP, right? So it's an LP. So you take the dual of this, it becomes a maximization problem, right? So this upper level is also maximization, the lower level is also maximization. By strong duality, this minimization problem is equal to the dual maximization problem objective. So you can directly, apply that, right? So this is the dual decomposition. This is the dual formulation. So the only difficulty with this problem is you have this term delta ij yk, which is a bilinear. It's not, it's not linear anymore. It's bilinear. It's non-linear because you're multiplying a continuous variable with an integer variable. So you need to, you can again, make it linear by using this vk term. So you have to write this additional constraints. So this is like, use this big M. So if zk is 1, then vk is less than equal to mk, and vk is greater than equal to delta ijk. So you want to minus vijk, so vk will take this value delta ijk. If zk is 0, then vk will take the value of 0, right? So this, you can easily verify this. So this is a linear version of the same problem, but we are using this big M. So we need to find some good value for big M. So we are proposing some good value for big M. So for any ij, if you find this value, then use this for big M, so you'll get a better LP relaxation. So this is one way of doing it, right? So the other way of doing it is like you replace the lower level problem, the minimization problem, by a constraint. So that what you will be doing is that problem will look like this. So you will want to maximize this subject to the constraint and all the same. Then you have a constraint known as closest assignment constraint. Closest assignment constraint, what it says is, if a particular path is there, then you should either route through the path or through a path which is cheaper than that. That is what closest assignment constraint says. So we'll propose, we have, in this paper, we are proposing 5 different closest assignment constraints. So this is the first constraint. What this constraint says is, if path k and m are present, which means zk and zm are 1, right? So the right hand side becomes 1, zk plus zm minus 1. So the left hand side, xijqs is all this path dijqs, which is lesser than the dijk, right? And this is for the path dijk. So what it says is, if zk and zm are 1, which means the path is present, the path dijk is present, so this term, the left hand side should be greater than equal to 1, which means route through some path which is cheaper than this path. Okay, so even though the problem is maximization problem, by adding this constraint, you are forcing the computer to choose the shortest path, right? So that is what this constraint is doing. So like when zk and zm are 1, so you have to route through some path which is cheaper than the current path. So this is the first constraint. The next one is like the totally reverse. So if zk and zm are 1, right? So the left hand side becomes 0. So right hand side becomes 0. 2 minus zk minus zm is 0. So then don't route if zk and zm are 1, means like the path dijkm is there, right? It is present. Don't route through some dijqs, some qs which is greater than this. So that is what this is saying, right? So if dijkm path is there, the cheapest path which is present, so don't route through something costlier than this, right? So that is what this constraint is saying. The third constraint also says a somewhat similar thing. So here what it says is, if this path zk and zm are present, right? So this term becomes 1. So it's m minus dijkm. So like, so you will get some difference, m minus dijkm. So this should be less than equal to m, right? So this term should be at least equal to dijkm, right? So either you route through dijkm or something cheaper than dijkm, but do not route something greater than this, right? So it is, in a way, what it is doing is it is enforcing that lower level problem, which is minimization problem, by means of this constraint, right? So we can use this constraint here, and you can have a single level problem. So each of these 3 constraints can be used here, and you'll get a single level problem, right? So single level problem, you can again solve it easily using Cplex. So like, so there is like, in the paper, there are some, like, I like this proofs very much. But like why, I'll explain you why we are doing this proof. So dominance relationships. So you have this 3 single level formulations, right? Based on CSE1, CSE2, CSE3. So I need to find out which one is good, right? Which one is good for me to solve. So like, how will I find which one is good? So whenever I give an MIP to a solver, so it is going to use branch and cut, right? So branch and cut, the first step, what it is going to do is, it is going to relax the integer problem as a LP problem. So you are getting LP relaxation. So, so this problem is a maximization problem. The LP relaxation, what it is going to do? It is going to give you what? It is going to give you one. Um, so if this is the integer objective, the LP relaxation is going to give an upper bound, right? So it is going to give an upper bound. So which one gives better upper bound? Whether the CSE one gives better upper bound, the CSE 2 or CSE 3, right? So in a way, this can be translated to which one is a subset, the LP feasible region, which one is a subset of the other, right? So that is what we are finding by this dominance relationship. So our proposition, there are like several proofs which is given in the paper. So what it says is like CSE2 is equivalent to CSE1, which means both LP feasible regions are the same. So if you solve the LP relaxation, you get the same objective. CSE2 dominates CSE3, which means CSE2 gives a better upper bound than CSE3. Right. So this like, if you are interested, you can read this paper, but I'm, for want of time, I'm not discussing these proofs. Right. So like what we are expecting is CSE2 should solve faster than CSE3. So because it is dominating CSE3, it is giving better upper bound, so it should solve faster. Right. Then further, what we do is we also reduce it, reduce the number of constraints in this CSE2 and CSE1 by using this possibility. So you take two paths, IJKM and IJMK, right? So if IJMK is greater than IJKM, then you need not, write IJMK constraint at all, because whatever comes in the left hand side, right? Whatever comes in the left hand side for IJMK will be contained anyways in IJKM, right? So like one constraint is better than the other, because both IJKM and IJMK, they both have the same RHS, which is 2 minus ZK minus ZM. One has 2 minus ZK minus ZM, another has 2 minus ZM minus ZK. The left hand side only varies, right? So like left hand side, we prove that, like, this, when this when DIJKM is less than DIJMK, the CSE to IJKM dominates CSE to IJMK. So you need not even write this constraint. So you get reduced number of constraints. So similarly, we write for CSE1 also, right? So this, based on this, now we have given like 5 formulations, right? 5 formulations based on CSE. Another is like one based on dual. So we are testing it on like CAP dataset and AP dataset. So I'll just show you the computational results. So this is the computational result. You can see that, this RCAC2 is the best one. So it is always marked in this bold color, right? So this is the best one because CAC2 gives the better LP relaxation, right? And RCAC2 has fewer number of constraints. So that you can see in this table, fewer number of constraints than other one, right? So RCAC1 and RCAC2, they have fewer number of constraints than their counterpart, CAC2 and CAC1. So dual, this is the data. So dual is not that fast for solving this small level problem. This is 25 node problem. So when you go for large problems like 100 nodes, 200 nodes, the dual formulation is very good. So you can see that it is solving within this 36,000 seconds, which is 10 hours. Whereas this RCAC2 and RCAC2, the best formulations in the upper level, the 25 node problem, they are not able to solve some instances, right? Now, like, this 200 node, none of these formulations, they could not solve within like this reasonable time. So we are writing a different algorithm known as Bender's decomposition algorithm. So Bender's decomposition algorithm is like, it's used for MIPs. So you decompose the MIP into an IP, a master IP, and a subproblem LP, and you solve it iteratively till you get the solution, right? So because you're decomposing it and you're doing it, you can do a lot of improvements on Bender's decomposition, so it solves faster. So I'll just show you for CSE2. I'm not going to touch the entire Bender's decomposition for all CSE2 or CSE2 and dual formulation. So this is my CSE2 formulation, right? So this is my integer variable, right? And this is one integer variable constraint. This is one integer variable constraint. So I'm separating this problem as a master problem and a sub problem. So master problem is maximize theta such that summation zk p minus r is equal to p minus r zk this, right? So this is my master problem. Then the sub problem is the remaining problem. The sub problem For the subproblem, you have zk, but zk is coming from the master problem. The solution zk is coming from the master problem. So this zk bar is a parameter. It is not a variable, right? So this is like a pure LP because this is a parameter. So this is a pure LP. Now you see this master problem is also maximization problem. The subproblem is also maximization problem. Now if I take dual of this, so I get minimization, right? I get minimization problem, right? So the master problem is a maximization problem. It's a part of the original problem, right? So this is going to give an upper bound. When you solve this problem, it is going to give an upper bound. The dual problem, this is a minimization problem, right? It's a minimization problem. So this is going to give a lower bound to the optimization. So original approach. So lower bound to the original problem, original MIP. So like for each master problem zk, so suppose I solve this master problem and I get this zk values, right? And I give this to here. So I solve this. Now there is another reason why I write this dual. Why I write this dual is like because now when I take dual of this, so this zk which is in the right hand side, they will all go to the objective function of the dual, right? So because the constants will go to the objective function. So now when the objective zk is in the objective function, the lower level constraint, right? The feasible region is independent of the zk, right? So for any zk, the lower level constraint set is the same. The feasible region of the lower level problem will not change. It is independent of the zk, right? It is independent of zk because you can see that zk doesn't come here. Because it is the same, so you can add a cut to the master problem, right? So you can add a cut to the master problem for each solution of the subproblem. So first I will solve the master problem, get the zk values, pass it here. I will solve the subproblem. Then I will add a cut which is nothing but this objective function, right? So theta is less than equal to summation this, which is the objective function of the lower level problem. But this one is like now these are parameters which is coming from the subproblem, right? So the master problem will have each iteration, I will add a Bender's cut, right? So I'll get an upper bound, I'll get a lower bound. So when they both converge, when I add sufficient cuts, which will make it, make them both converge, then I'm getting the solution. So the procedure is like this: while upper bound minus lower bound is less than some epsilon, first you solve master problem, right? You solve master problem, you get zk, you solve sub problem, right? So then from the solution of sub problem, you add a cut to the master problem, Bender's cut to the master problem. So you update this upper bound and you update this lower bound. So you will, the upper bound and lower bound will be like this. Then slowly they will converge and they will meet together, right? So this is how this Bender's decomposition works. Like means we don't have a lot of time to deal much on Bender's decomposition. So, but this is like I'm just giving the broad picture on Bender's decomposition, right? And this is just Bender's decomposition for CaC2. So in the paper there is for RCaC2 and dual is also given. So you can look at the paper. So this is the results. So you see, Bender's decomposition is like very, very fast for this large problem. So you see that, this case 200 nodes, 10 hubs. So it is like 21,000 seconds it is taking. So here it is just solving in 5,779 seconds. So it's like almost 4 times faster, 5 times faster, 22,000. Here it is just 3,300, which is like almost how much? 6 times, 7 times faster. 19,000, 2,200, which is again 9 times faster. So Bender's decomposition is very, very efficient when you are like, you are solving large problems. So like with this, like, we are closing hub interdiction problem. Now we'll go to hub protection problem. So hub interdiction problem. So like what we did, so like we formulated a bi-level problem, then we reformulated as a single level problem, like using multiple ways, and we saw like we identified which one is best, right? We theoretically studied the their properties and see that some formulation is better, and our computational results also proved that. Then we did a Bender's decomposition to solve large scale problems, and the Bender's decomposition is able to solve large scale problems very efficiently, right? So this is our contribution in hub interdiction problem. Now going to hub protection problem, this is like a one level above this interdiction problem. So this is your basic interdiction problem, right? So knowing that the defender right? The defender is a network operator. He knows that that is an attacker who is going to attack my network, so he can put some resource to protect some hubs, but he cannot protect all the hubs. So the idea is, if I protect a hub, the attacker is not going to attack my my network, right? So that particular hub. So here he is interested in finding minimizing the attacker's interdiction cost, right? So he wants to minimize the attacker's objective. The attacker's objective is to maximize the defender's routing cost. So the first level is a defender, the second level is an attacker, the third level is a defender. So the first level, he wants to protect some hubs so that he will minimize the interdiction cost. He wants to minimize the maximum interdiction cost. The attacker wants to maximize the minimum routing cost. So it is like a min-max-min problem. Min-max-min problem. So how they are doing it? He is going to minimize the maximum interdiction cost by protecting sub-hubs. So if you protect some hub, the attacker cannot attack that hub. Now, so initially you had P hubs, right? Now, because now he has protected it, the attacker cannot attack some hubs. So out of the remaining unprotected hubs, he is going to attack R hubs, which will maximize the third level cost, which is minimize the routing cost. So like now P minus R hubs is only remaining. So he will route through the remaining remaining hubs. So that is the idea. So this problem is a tri-level problem, right? So this is the upper level objective, minimize. You want to protect U hubs. The lower level one, this is the attacker's problem, this is the defender's problem, this is the attacker's problem, this is the defender's problem. So the defender, he wants to protect U hubs. The attacker wants to attack R hubs. So the 2, 3 are those constraints. It's summation k zk is equal to P minus R. So if yk is 1, which means if it is protected, then zk can be 1. Zk is surviving hub, right? If yk is 0, if it is not protected, then zk can be anything, right? So it can be attacked or anything. So the lower level problem is like the same as interdiction problem. So we use a method which is known as an implicit enumeration method to solve this problem. So this is based on the observation that if I solve a pure HIP, which is hub interdiction problem, at least one of these hubs will be protected in the protection problem, right? So that is because, like, if I don't protect anything and I solve the problem, so it's a hub interdiction problem. So I'm interdicting a certain hubs 1, 3, and 5. So at least one of them should be protected, because the protection problem should have objective lesser than this. So this, based on this property, so we build this algorithm. So first at root node, we solve a hub location problem. So the table is given here. So initially you had the hubs 1, 2, 3, 4, 5. So 5 hubs. You want to interdict 2 hubs and protect 2 hubs. Okay. So I am solving a hub interdiction problems. I interdicted 2, 3 hubs. The objective is 100, right? So now I'll branch with y2 is equal to 1 and y3 is equal to 1. So based on this property, solution of hub interdiction problem, at least one of the subs will be solution to the protection problem. So y2 is equal to 1, y3 is equal to 1, which is like protected. So then I get node B and C. Node B and C. So node B, then because 2 is protected, the attacker cannot attack 2. So he will just get 1, 3 interdicted hubs. Because 3 is protected, he cannot attack 3. So he has to get this, interdict 2 and 5. So this is my objective. My objective is improving. See, he wants to minimize the maximum cost. So the maximum cost is 100. So we are minimizing it now. So now, again, 1, 3 and 2, 5 will branch. y1 is equal to 1, y3 is equal to 1, y2 is equal to 1, y5 is equal to 1. And I get different solutions, right? So I have reached my number of hubs to protect is 2, right? Number of hubs to protect is 2. So I have like four possibilities, and I'll see which one is the cheapest one. And that is a solution to my protection problem. So at optimal solution, you will be protecting hubs 3 and 5, and the attacker will interdict hubs 1 and 2. Right. So like the detailed algorithm is given in the paper. So this is just a schematic. So you can see that, one is like you can enumerate all possible protection combinations. So you'll see that this is the time it will take. Whereas this implicit enumeration is very fast, and you are getting a lot of reduction in this computational time, and you can solve problems up to like 100 nodes, right? So so this is about yeah. So that finishes our protection problem. So in summary, like in this paper, we studied a bi-level HIP and tri-level HPP, which is hub protection problem, hub interdiction problem. So these problems are NP hard problems. They're very difficult problems. So like we proposed like several reformulations and exact methods to solve this problem. Also, this implicit enumeration, like we use this lower level. This at any point you are solving a interdiction problem at each node. So you have a single master problem and you will use like multiple sub problems. So we have used those techniques in the paper, and that is like it's even more faster than directly solving using some algorithm. Yeah. So like we also proposed a Bender's decomposition algorithm and implicit enumeration algorithm to solve these problems. So our goal was to solve large scale problems, and we solved large scale problems in this paper, right? So that is the contribution of this paper. So like okay, thank you. So I think we are done. So like I have just went through a bit fast because like I'm not very sure like how much you understood, but if you have any doubts you can ask me, right? So I'll be happy to help you out.
So we will take up questions now. In case of any queries, please raise your hand. We will take them up one by one.
Aditya, can I make a meeting? Hello?
Yes, sir. So please.
Yeah. Prasanna, congratulations for a lovely presentation.
Okay.
That's my first observation. Of course, the older you get, maybe less mathematical I become. But one or two things which I would like to comment on. Uh, is this hub and spoke, like you have got multiple facility location problem? So how many such new facilities there should be, and that will bring in your location allocation problem. So here, whether your hubs are 2 or 3 or 4, how many, is that also a decision problem?
Okay. So like this problem is like you can see this is a location routing problem.
Let me ask you one more thing. The
Okay.
attacker defender, this gives the idea of a game theoretic type of a situation, that
Yeah.
there is the attacker and the defender. But supposing there are multiple attackers and multiple defenders, is there any way to then convert them into attacker defender?
Yeah. Okay. So, sir, I'll answer both of your questions. So, first is this problem is like it's like a special form of facility location problem where it's like a location routing problem. So, not only we locate hubs, right, but also like we are also deciding this XIJKM, which is the path of the route we have to take, right? So that is one thing. And this problem assumption is like you can have only at the max 2 hubs between a source and destination. Between I and J, you can have only 2 hubs. So that is the the one assumption in this work. Another one thing, you were asking about multiple attackers and multiple defenders, right? So that will be like means more even difficult problem to solve. That is because like in that case you'll have like several levels.
That is that.
So if everyone has the same objective and then it is like you can model it in like 2-3 levels. But if they have different objectives, then it becomes like multi-objective problem, multi levels, right? That is more difficult to solve.
Now, when these hubs, that protection thing that you're talking about,
Yeah.
like there is, like when you open new facilities, we talk about the fixed cost. The more the number of new facilities located, fixed costs go up, but the transportation cost coming closer to the consumer, that comes down. Now, is there any fixed cost of your hubs that you're creating?
No, this we are not assumed like you can have a fixed cost component also. So here we are using that cardinality, right? So like we are saying like you locate P hubs, you protect U hubs, but you can say like there is a protection budget. So I have this much budget. So out of this budget, this is the cost of protecting this hub. This is the cost of protecting this hub. So like that will be a different variant of the same problem, and people have studied those problems in facility protection literature.
Okay. I have one last thing from my side. When you're talking of the distances,
Yeah.
is it shortest distance, Euclidean, rectilinear?
Yeah, this is Euclidean.
Euclidean, is it?
Yeah. Yeah. So like so the data sets which we study, right? One is civil aeronautics board, it's CAB data set. So this is data set, like they take this yard distances. Another is Australian Post. Australian Post is like that postal network of Australia. So they have released a data set. So that one we use, right? So like, but we assume that it's the Euclidean distance. It follows triangle inequality.
Thank you, Prasanna.
Thank you,
And
sir.
as you know, in the MBA program, we have marks for class participation. So I hope I participated in your class.
Yeah.
Thank you.
Thanks.
Thanks.
Thank you, sir, for questions.
Thank you, Professor Bandit. Do you have any other query? Okay, so I think we do not have any other further query. So in that case, we can end this session now. And thank you, Professor Prasanna, for such an informative presentation. I'm sure most of us will benefit from this presentation of yours. And thank you everyone for joining.
Okay, I'll just make one final recommend. So like, except Professor Bandit, nobody asked me. So either you understood everything or you didn't understand anything. But I hope you you get something out of it. But this is a very interesting research area because like not many people work here, and because it's very difficult. That's why people don't work in this area, right? So like, so if at all you are interested or you have some doubts in the paper only, so you wanna ask, you can always mail me and ask any doubts. Right, so that is not a problem, but yeah, so if this is a to sum it up, this is this is a nice area to work on, and it's very you like writing these proofs, and yeah, so okay, thanks for the opportunity.
Thank you, sir.
Thank you. Bye.
Would request the team members to please stay back.
Okay, I leave, right?
Yes, sir. Thank you very much.
Thank you. Bye.